Hello and welcome to the chapter 13.3 lecture on dot products. Before we begin this though, I think it might be a good idea to go over two of the typically most missed homework problems from the 13.1 to 13.2 homework. If you feel that you aced the homework and these problems, feel welcome to skip ahead. So this one from 13.1, let U be A4 and B be 4, 6. First, find the value of A such that U is parallel to B. So recall that two vectors are parallel if and only if one is a scalar multiple of the other. So U is parallel to V if U is equal to CV or V is equal to CU or some scalar C. And by a scalar, we mean a real number. So what we want is that A4 is equal to C times 4, 6 or some scalar C, but, well, scalar multiplication distributes. So that's the same as being equal to 4c comma 6c. And two vectors are equal if and only if their respective coordinates are equal. So what we can conclude from this is that A is equal to 4c and 4 is equal to 6c. Since for these to be equal, A must be 4c and 4 must be 6c. And this is a system of equations that we can solve. So taking the second equation, that implies that C is equal to 4 sixths, which is 2/3. And then taking the first equation, that means that A is equal to 4C, which is 4 times 2/3, is 8/3. So we have solved for A, and what this means is that 8/3 4 is parallel to 4, 6. And in fact, specifically, 8/3 4 is equal to our scaling factor C, which was 2/3, times U, which is 4, 6. And you can check that 2/3 times 4 is 8/3, and 2/3 times 6 is 4. Now, the second part of the problem is finding perpendicular vectors. And it tells us that two vectors are perpendicular if and only if they satisfy this equation. This left-hand side is in fact a dot product, which is the subject of today's lecture. But for now, while on the homework, they just give us the equation and we need to work with that. So part B, we want this equation, and U is this, B is that. So plugging in the numbers, we want A times 4 plus 4 times 6 to be equal to 0. And that means that 4A plus 24 is equal to 0. So therefore, A is equal to negative 24 fourths, which is negative 6. So that means that negative 6, 4 is perpendicular. That's the perpendicular sign to 4, 6. And indeed, we can check that it satisfies this equation. That's negative 24 plus 24, plugging it into that equation, which is 0. Now, the last homework on 13.2 was this problem. Determine values of x and y such that these 3 points are collinear, which means lie on the same line. So, in other words, where that's B, that's W, and that's U, we want that these 3 points lie on the same line, like that. So, how do we find x and y such that this is true? Well, if this is true, imagine this vector. To get to this point here, we need to take this vector and stretch it. And this vector is W minus V, where that's our point W, and that's our point V. So W minus V, oh, by the way, if we want to be very technical, you want to imagine this on the Cartesian plane and think of these points as themselves vectors. So for example, the W vector is this point, or this vector, and the V vector is that vector. And that vector difference is this red vector W minus V. So anyway, W minus V, thinking of these as vectors, is 7, 5, 1 minus 1, 2, 3, which is 6, 3 minus 2. Now, what we want is for us beginning at V, we want to be able to add W minus V, but stretch by some factor such that we get to this point U. So we want it to be the case that B plus some scalar times W minus V is equal to our point U. So plugging in, we have that 1, 2, 3 plus C times 6, 3 minus 2 is equal to U, which again, thinking of U as a vector in the same way, is x, y, 2. So distributing that C and adding these together, we have the equality that 1 plus 6C, comma 2 plus 3C, comma 3 minus 2C is equal to x, y, 2. Now, as always, two vectors are equal if and only if their respective coordinates are equal. So setting their respective coordinates equal, we have 1 plus 6C is equal to x, 2 plus 3C is equal to y, and 3 minus 2C is equal to 2. So this is a system of equations where we can solve for C. So solving for C in this last equation, that implies that C is equal to, so 2 minus 3 is -1, divided by -2 is 1/2. So now that we know that C is 1/2, we just plug it into each of these equations, and we therefore get that x is equal to 1 plus 6 times 1/2, and y is equal to 2 plus 3 times 1/2. And finally, that means that x is equal to 1 plus 3 is 4, and 2 plus 3/2 is 4/2 plus 3/2 is 7/2. So now let's begin talking about the dot product. So first, recall that the magnitude of a vector means its length, and we compute the length using the Pythagorean theorem. A squared plus b squared is c squared. So c is the square root of a squared plus b squared expressed with vectors where v1 and v2 are the respective coordinates of the vector. That's the square root of v1 squared plus v2 squared. And these magnitudes satisfy certain properties, one of which is the triangle inequality. It says that the magnitude of u plus v is less than or equal to the magnitude of u plus the magnitude of v. This is due to the following. If we imagine that this x, for example, is in fact u, and that y is v, and this is therefore u plus v, using our geometric understanding of vector addition, well, the hypotenuse cannot possibly be longer than the sum of the lengths of the two sides. So this is the hypotenuse, and that cannot possibly be longer, so it's less than or equal to the sum of the lengths of the two sides. And magnitudes also satisfy what we call absolute scaling. So the magnitude of CV is equal to the magnitude of C times V. And the reason that we need this absolute value sign around C is that C might be negative, but magnitude is always positive. So the dot product. We'll introduce the dot product first geometrically, and this geometric understanding of the dot product is vital throughout the class to understand and visualize what it means. And after this, we'll present the algebraic definition of the dot product that is equivalent to this geometric understanding. So u dot v geometrically is the magnitude of u times magnitude of v times the cosine of theta, where theta is the angle in between them. So first, why do we care about the dot product in a physical sense? Well, in physics, work is force times distance. So here is illustrated a block, and we exert a certain force on it, pulling the block into a different position, and the work done is force times distance. But what if our force vector is not in the direction of motion? Well, the component of the force vector here that's pointing up, the block doesn't move up at all. So that part is irrelevant. It's like plus f times 0, or plus a component of f, some number times 0. What we care about is this guy. That is the component of f that is actually in the direction of d. And that is the magnitude of f times the cosine of theta by trigonometry. And then the total force done is this component of f times the distance, for force times distance, and that is this times the magnitude of d, and we end up getting the very formula that for dot product up here. So therefore work is in fact the force vector dot the distance vector. So let's explore this geometric understanding of the dot product and do some examples. So as this illustrates, u dot v is the length of the projection of u onto v multiplied by the length of v. Let's draw a picture to better understand this. So here is u. Imagine that there's v. The length of the projection of u onto v. So that word projection means that we make a right triangle here, and this guy is the projection of u onto v, and we denote it that way. So again, this symbol means the projection of u onto v, and it's that red arrow. And the dot product is geometrically taking the length of this red arrow, the projection of u onto v, and multiplying it by the length of v. So u dot v is equal to the magnitude of the projection of u onto v times the magnitude of v. So let's do some examples. So if u and v are parallel, then that means that the length of the projection of u onto v is just u. So in this case, u is the projection of u onto v. And therefore, u dot v is just the magnitude of u times the magnitude of v, because this guy is the projection of u onto v, in this case, where they're parallel. If they are at some angle, then we have this, and again, this guy is the projection of u onto v. And what is the magnitude of that projection of u onto v? Well, by trigonometry, it's going to be equal to the hypotenuse, which is u, times the cosine of that angle theta between them. So u dot v is in general the projection of u onto v in magnitude times the magnitude of v. And that therefore is by this magnitude of u times cosine theta times the magnitude of v, which is u in magnitude times v in magnitude times cosine of theta. And look at that. That is the same formula from the previous slide over here, and that is why this is an equivalent way of thinking about it, as the projection of u onto v times magnitude of v. It is that same formula working it out using trigonometry. And finally, in the example that u and v are perpendicular, then the projection of u onto v is 0, the 0 vector technically. It's just a point. So therefore, u dot v is 0, since that magnitude of the projection is 0, and 0 times anything is 0. Okay, so that's interesting. And recall the first homework problem that we worked through in this lecture, finding with the formula for when two vectors are perpendicular. Well, it fundamentally comes from this. Two vectors are perpendicular if their dot product is 0. We'll get into that more in a bit. Okay, and two more examples. What if u is positioned like this with an angle that greater than 90 degrees, which is the same as greater than pi over 2, which we'll typically be using gradients? Well then, what does the projection look like? The projection of u onto v, in this case, looks like this. So this guy is the projection of u onto v. And by trigonometry, it still satisfies the same equality, except now, well, cosine is negative in the second quadrant. Now imagining the quadrants like this. So therefore, in this case, where they are at an obtuse angle, the dot product will always be negative. This is negative in quadrant 2. And finally, if u and v are parallel, but facing in opposite directions, then in the same way as over here, it'll just be their lengths multiplied, except now the cosine of theta is negative. Specifically, the cosine of theta here is the cosine of pi, which is -1. So u dot v is magnitude of u times magnitude of v times cosine of pi is negative magnitude of u magnitude of v. So I introduced it this way for a bit of simplicity, but technically we need to add a plus or minus sign, and it is negative if the angle is obtuse. But if the angle is acute like this, then it's positive. And just remember that if the angle is obtuse, then it's negative. So let's do an example. Suppose that u and v are unit vectors. Remember that unit vector, that means that they are both of magnitude 1, and that the angle between them is 2 pi over 3. So let's visualize this. And we can always think of vectors as in standard position, and we may as well think of our vector u as being like this, where that's 1. If it isn't like that, then we can just swivel everything about so that u lies on the x-axis. And to be clear, that'd be 2. There is 1 again, that's -1. This is the Cartesian plane. And both of them being unit vectors means that they lie within the unit circle. Pretend that that's a circle. And v, it forms an angle of 2 pi over 3 with u. So this guy here, that angle is 2 pi over 3. And v looks like that. So we know that it's going to be the projection of v onto u times the magnitude of u. And in this case, the angle is obtuse, so it will be negative. Okay, so what is the projection of v onto u? So this purple vector here is the projection of v onto u. And what is that but the cosine of theta? And that comes from, well, remember your trigonometry, that's the cosine of theta and that's because it's adjacent over hypotenuse times hypotenuse, but hypotenuse is 1 since they're unit vectors. So we just have adjacent over hypotenuse, which is the cosine of theta. And the cosine of 2 pi over 3 is -1/2. So therefore, u dot v is negative that projection of v onto u times the magnitude of u, and that is negative absolute value of -1/2 times 1, since u is a unit vector. And that is -1/2. So note that two vectors u and v are parallel if and only if their dot product is plus or minus the magnitude of u times the magnitude of v. That comes from what we worked out earlier here. That's when they're in opposite directions with the negative, and that's when they're in the same direction, and then the dot product is positive. But in both cases, magnitude of u times magnitude of v. And similarly, by what we saw, vectors u and v are orthogonal, which is another word for perpendicular, if and only if u dot v is 0, since then the projection is just a point. And that's the 0 vector, and 0 times anything is 0. Let's do another example geometrically. So our vector u, root 3 is about 1.7. So, but u looks like that, going to root 3, comma 2. And v is 2, 0. So v looks like that, going to 2, 0. So we want to project u onto v, and this guy is the projection of u onto v. And what is that? Well, the projection of u onto v is, by trigonometry, equal to the magnitude of u, that's the hypotenuse of this triangle. Recall that this is a right angle, so that's the hypotenuse times adjacent over hypotenuse, which is, well, cosine of theta. And we could think about it this way, but it's easier to just use the coordinates. I mean, after all, the x-coordinate of u is this projection. That's the x-coordinate, that's the y-coordinate. So this is root 3 in magnitude, and the angle is acute, so there is no negative sign, it's positive. Again, this is just the x-coordinate of u. And in general, it's not going to be the x-coordinate of u if v does not lie on the x-axis, but in this case, v lies on the x-axis. Okay, so u dot v is the magnitude of the projection of u onto v times the magnitude of v. But v is, as you can see, simply of magnitude 2. It's of length 2. So we have root 3 times 2, which is 2 root 3. Okay, and our last geometric example. Let u be 2i plus 3j and v be 4k. And remember that k means the coordinate in the z direction. So what does this look like? There's our x-axis, that's our y-axis, and perpendicular to both is our z-axis. So u is 2i plus 3j, so u looks like that. And v is 4k, so v looks like that. So what is the projection of u onto v? Well, because u lies on the xy plane and v is perpendicular to the xy plane, they're perpendicular vectors. And remember that the dot product of perpendicular vectors is 0. After all, if we take u and project it onto v, then we just have a single point. So the projection of u onto v is the 0 vector, and thus u dot v will be 0 times something, and that is 0. So now that we understand dot products geometrically, we can move on to the algebraic definition. But again, this geometric understanding is absolutely vital for understanding what any of chapter 17 is, and well, much of chapter 14 as well. So fortunately for us, we don't have to do this way of thinking for dot products in general. We just need to know that this is what the dot product is geometrically, and we can compute it using this much simpler formula. Given two vectors, u1, u2, u3, and v1, v2, v3, the dot product is u1, v1 plus u2, v2 plus u3, v3. So we just multiply their respective coordinates and add them together. So, for example, 2,3 dot negative 5, 2 is 2 times negative 5 plus 3 times 2 is negative 4. And what is the geometric meaning of this? Well, first, it is negative. So the angle between them is greater than pi over 2, i.e. obtuse. And, well, it's the projection of negative 5, 2 onto 2, 3 multiplied by the length of 2, 3. And it's negative because the angle is obtuse. Now, what is a vector dot itself? Well, computing this, multiplying their respective coordinates and adding together, that's a times a plus b times b plus c times c. This is ordinary multiplication, not dot products. And that is a squared plus b squared plus c squared. Oh, that looks familiar, doesn't it? The magnitude of a vector is the square root of the sum of the squares of its coordinates by the generalized Pythagorean theorem. The magnitude of a vector ABC is the square root of a squared plus b squared plus c squared. And that means that if we square the magnitude, we get a squared plus b squared plus c squared. And that guy is the dot product of the vector with itself. So the dot product of a vector with itself is its magnitude squared. And we can use our geometric understanding of dot products in tandem with our algebraic understanding to find the angle between vectors. And that's pretty cool and useful. So as always, let's imagine our Cartesian plane. 1, 2 looks like that. And 2, 1 looks like that. And we are interested in what this angle theta is. That's a non-trivial problem, and one that we couldn't really do before we learned about dot products. But through dot products, since this angle is acute, we know that the dot product of 1, 2 and 2, 1 is equal to, well, the magnitude of u times the magnitude of v times the cosine of the angle between them. Look at that. We know how to compute this algebraically. We know how to compute these magnitudes, and then we can solve for the cosine of theta and thus theta. Okay, so this left-hand side is 1 times 2 plus 2 times 1. And the right-hand side, well, the magnitude of 1, 2 is the square root of 1 squared plus 2 squared. We're multiplying that guy by the square root of 2 squared plus 1 squared, which is the same thing, and multiplying that by cosine of that angle theta that we want to figure out. Okay, so this is 4. The square root of 1 squared plus 2 squared is 5, and both of those are the same. So we have the square root of 5 squared times the cosine of that angle between them. And therefore, the cosine of that angle between them is 4 divided by 5, 4/5. And thus, theta is the arc cosine of 4/5. Pretty neat and very difficult to figure out without dot products, but quite slick with them. So now let's learn some properties of dot products. So first, dot products are commutative. Remember that commutative means you can swap the order and you get the same thing. And this follows quite directly from our algebraic definition of the dot product. And similarly, C times U dot V is the same as CU dot V is the same as U dot CV. So we can distribute a scalar into either the U component or the V component, but not both at the same time. And U dot V plus W is U dot V plus U dot W. That's distributive, so dot products behave like ordinary multiplication in all of these senses. Remember that 0.2 is also like ordinary multiplication. And this note is actually what we figured out earlier, that V dot V, if V is ABC, is A squared plus B squared plus C squared. And the magnitude of V, as we know, is the square root of A squared plus B squared plus C squared. So squaring that magnitude, we have that it is V dot V. And therefore the magnitude itself is the square root of V dot V. So we can define magnitude in terms of dot products if we want to. And we will sometimes want to. Now, in introducing dot products geometrically, we already talked about the projection. These are called orthogonal projections in the sense that this angle is a right angle. And the projection of U onto V is denoted this way, as we know, and it is that vector. And likewise, if the angle between them is obtuse, then it is that vector. We just go in the opposite direction as V and project down. So we had been finding these orthogonal projections in our geometric examples by hand, where it wasn't too hard to find the orthogonal projection in those specific cases. But for example, in this problem, how would we find that orthogonal projection? Well, we can use our definition of the dot product and end up getting what the orthogonal projection is. And this orthogonal projection will be very useful. For example, in physics, where we began this lecture with how we would want to project the force vector onto the distance vector, and that is the orthogonal projection. Okay, so we know that U dot V geometrically is the length of the projection of U onto V multiplied by the length of V. So therefore, if we divide U dot V by the length of V, i.e. take U dot V over the magnitude of V, then that is the length of the projection of U onto V. So just dividing both sides by this length of V. And then if we multiply that length of the orthogonal projection by the unit vector in the same direction as V, then we scale that unit vector to be the length of the projection of U onto V and facing in the same direction of V, which is the projection of U onto V. So therefore, the projection of U onto V is U dot V over the magnitude of V, its length, times V over the magnitude of V, which is the unit vector in the desired direction. So rewriting this, we have that the projection of U onto V is U dot V over the magnitude of V squared times V. This V is still just hanging out there. But since the magnitude of V squared is, as we know, V dot V, we can in fact write it this way. Is U dot V over V dot V, that guy, times V. So this is the formula for orthogonal projection, big underlined font, because this is a very important formula in the class. So let's do an example. Let's find the orthogonal projection of 235 onto 122. So we know that the projection of U onto V is U dot V over V dot V times V, and it's just a matter of computing that. Okay, so that's 235.122 over V dot V, that's 122 dot 1, 2, 2. And notice that this whole guy will be a scalar. The dot product is a scalar, you just get a number out of it. Likewise, this is just a number. So we take that scalar and then we multiply it by v, and v is 1, 2, 2. Okay, so computing these guys, we have 2 times 1 plus 3 times 2 plus 5 times 2 is 18, over 1 times 1 is 1, plus 2 times 2 is 4, so we have 5, plus 2 times 2 is 9. Okay, times 1, 2, 2, that is 2 times 1, 2, 2. And a scalar times a vector, we just multiply every component. So we wind up with 2, 4, 4 is the orthogonal projection. So on a previous slide, we derived this formula for the dot product. And this guy here is the length with a possible minus sign up here if the vectors have an obtuse angle between them. And that is called the scalar component of u in the direction of v. So that scalar component of u in the direction of v is this guy, and it's just plus or minus the length of the projection of u onto v. After all, this is a unit vector, and that's the length of the projection with that possible minus sign if they're orthogonal. And that concludes the chapter 13.3 lecture. Best wishes, and have a good one.